Welcome to the second part of the lecture on biomechanics of the elbow joint. This is in continuation to the lecture on biomechanics of the elbow joint part 1 discussed earlier. So, we will be discussing on the part 2 of the problem that was being discussed in the topic biomechanical analysis of elbow flexion. Now, as mentioned in the previous lecture, the aim of the calculation was to define the magnitudes and directions of the joint reaction forces. Based on the geometry and the given data on muscle origin and insertion, the moment arm of each muscle action about the joint axis was calculated. Using these moment arms about the joint axis, the muscle forces were estimated. Now, since the muscle forces have already been estimated, the joint reaction forces of humeroradial and humeroulnar articulations need to be separately calculated. In the part 1 of the lecture, we had assumed that the radius and ulna to be one bone articulating with the humerus, and based on that assumption we had calculated the muscle forces. Now, we will be separately calculating the joint reaction forces corresponding to humeroradial articulation and humeroulnar articulations. So, first we consider the humeroradial joint. Now, for the calculation of joint reaction forces, the humeroradial joint reaction force, a further assumption is that the two bones carry an equal share of limb's own weight. Okay? So, we can see here that the limb weight is half in case of the radius articulating with the humerus. For the articulation between ulna and humerus, the other half of the limb weight will be considered. Now, this is the free body diagram of the muscle forces and the external loads along with the limb weight and the joint reaction force, which is the humeroradial joint reaction force. Now, we had already determined the angles at which these muscle forces were acting. So, we have already the values of gamma and beta. So, applying the earlier principle, which states the moment applied by the external loads is equal to the moment applied by the muscles about the joint axis at A. So, the moment applied by the muscles are the moment generated by the biceps and the moment generated by the muscle brachioradialis. So, Based on the moment arm, these moments individually can be calculated. Now, let us come to the moment created by the limb weight and the weight carried by the radius. Now, in this connection, we at this moment do not know what is the amount of weight carried by the radius. So, this needs to be first determined, but we can use the moment balance equation, the equilibrium equation, and determine the value of WR, which is the weight carried by the bone radius, which comes out to be 194.46. Now, the total weight carried by the elbow joint at 90-degree flexion was given as 311.25 Newton, out of which 194.46 Newton is taken up by the radius bone. The remaining part, that is 116.79 Newton, is carried by the ulna. Okay. So, now we proceed with this data, calculated data of the weight carried by the radius bone, and we resolve the system of forces along the vertical direction, and we can write down the equation based on the laws of equilibrium, summation of the forces along the vertical direction. Resolving horizontally, we can write down the equation, the RR, the component of RR sin alpha is equal to the muscle force brachioradialis muscle force, the component along the horizontal direction, that is cos gamma, and the horizontal component of the muscle biceps, which is FBI cos beta. The gamma and beta are the inclination angles of these forces. By equating the above two equations, we can actually calculate the tan alpha, which is where alpha is the angle of inclination of the humeroradial joint reaction force RR. So, alpha comes out to be, when we put down the values of the angles gamma, beta, as well as the external load WR, which is being carried by the radius bone, and the limb weight, half of the limb weight of course in this case, we actually can determine the angle as 17.2 degrees. Now, substituting this value in the equation formed by the horizontally resolved forces, we can determine the RR, that is the humeroradial joint reaction force, which comes out to be 1269.33 Newton. In the earlier slide, we had calculated the angle alpha is equal to 17.2 degrees, that is the angle at which the humeroradial joint reaction force is inclined. Now that we have calculated the magnitude of the resultant humeroradial joint reaction force RR and its inclination 17.2, its effect upon humeroradial contact can be considered. resolving RR into normal and transverse component. So, RR can be resolved into normal component Rn and RT, the transverse or the tangential components. We can actually find out the normal and the transverse or tangential force as indicated in the slide. Now, in this calculation, we need to note that the normal component Rn makes an angle of 60 degrees with the humeral shaft. So, the normal component Rn as indicated here, Rn actually makes 60 degree with the humeral shaft axis. So, if we have already calculated RR making an angle 17.2 degree with the humeral shaft axis, then the remaining angle is 42.8 degrees. So, with this angle 42.8 degrees, we can actually use it for calculation of Rn and Rt by resolving Rr along the Rn direction, normal direction and the tangential or transverse direction. So, the values of Rn comes to 931.35 Newton and Rt 862.44 Newton. The figure on the right presents a sagittal section of the humero-radial joint. So, similar to the vector diagram, here we are locating the vectors, normal vector, the tangential vector and the resultant vector in a figure representing a sagittal section of the humero-radial joint. Now comes an important consideration in the problem, that is on the calculation of the ligamentous force. Okay. On the right we can see a figure which presents an arrangement of the articulation, the elbow joint articulation. And if we assume an interface friction coefficient of 0.02, we can find out the frictional force at the point of contact as a function of the normal force that has been calculated as 931.35. So, the frictional coefficient multiplied by the normal force will give you the frictional force that is actually being generated at the point of contact, if we consider a frictional coefficient of 0.02. Now, this 18.63 Newton of frictional force is along the tangential direction. So, the original tangential component of the force was 862. So, 862.44 minus this value 863, the tangential the frictional force along the tangential direction, gives rise to a force 843.81 Newton that will actually cause sliding, and physically what will happen, this force, the balance this unbalanced force of 843.81 Newton along the transverse direction will tend to move the radial head sidewise across the capitulum. So, the radial head will be pulled sidewise across the capitulum due to the action of this unbalanced force. of 843.81. However, this is not the case in reality, because the force is taken up by the ligamentous system, which restores the radial contact to equilibrium. So, it will be further assumed that the forces Fl, which is the force of the ligamentous system, and the RT, the force along the reaction force along the tangential direction are coplanar. Now, if we further consider the action of the ligamentous force, the force imposed by this ligament Fl is assumed to act as shown in the figure. A free body diagram is given in the figure. It is equal in magnitude, but opposite in direction to the sliding force set up at the point of contact. The sliding force is the remnant force that we had calculated earlier, the unbalanced force, by subtracting the RT minus the frictional force. So, by subtracting the frictional force from the original tangential joint reaction force, the tangential component of the joint reaction force. Now, as these two forces are not collinear, they will impose an extension moment on the radius. Now, it is assumed that the combined component of the ligaments act at a distance of 0.08 meter from the joint axis at A and along the radial shaft. So, it is along the radial shaft and at a distance of 0.08 meters, and it acts at an angle of 30 degree to the humeral axis. So, this is a data that is assumed for the purpose of calculation. Now, we should recalculate the humeroradial joint reaction force considering the effect of the ligamentous force. So, assuming the combined component of the ligaments act at a distance 0.08 meters from the joint axis along the radial shaft, the moment imposed upon the radius is calculated as 58.46 Newton meter. The moment opposes the flexion muscle arrangement and therefore reduces the load that can be carried. The resultant has to be calculated once again, since a portion of the transverse component of the reaction force is taken up by the ligamentous system. So, if we see a transverse view of the point of contact between radius and the humerus, we can see the RT, the transverse component, the normal component at the point of contact, and of course, the resultant humeroradial joint reaction force along the direction as shown. Now, the normal component of the force Rn, as shown earlier in the figure, remains unchanged and is calculated as 931.35 Newton acting at an angle 60 degrees. So, this is 60 degrees to the humeral axis. So, the normal component of the joint reaction force remains unchanged in direction and magnitude. However, the transverse component or the tangential component RT has its direction unchanged, but now the magnitude is equal to the frictional force that has been calculated earlier in slide 8. Please visit slide 8 for calculation on the frictional force, that is 18.63, and this frictional force is basically now the tangential component of the joint reaction force. So, once we have these two data, we can recalculate the revised humeroradial joint reaction force as 931.54, and the angle x, the inclination of this resultant force with the humeral axis, can also be calculated, which is 58.85 degrees. The next important step is recalculation of the load carried by each bone, because now we have the ligaments acting in the system. So, separately we will consider the radius bone and the ulna bone. Previously, a load of external load of 194.46 at a moment arm of 0.35 was assumed, giving rise to a moment of 68.06 Newton meter. So, the calculations, for the detailed calculation you can refer back to slide 5. This was previously the load, the moment arm, giving rise to the moment 68.06. Now, if we subtract the moment of 58.46 Newton meter imposed by the ligament, see calculation in slide number 10, then we are left with an unbalanced moment of 9.6 Newton meter, or a load to be carried. If we divide the moment by the distance 0.35, then we recalculate the load carried by the radial segment of the bone, which is 27.43 newtons. So, we recalculate the load carried by the radius. Earlier it was 194.46, now it is 27.43 newtons. It has reduced. For the ulna bone, the load was earlier estimated to be 116.8 Newton, acting at a moment arm of 0.35 meters, resulting in a moment of 40.88 Newton meter. For detailed calculation, please see earlier slide number 5. Now, the revised moment can be calculated as, so it was earlier 40.88 plus the moment imposed by the ligaments. The two moments are added, giving rise to a new moment of 99.34, corresponding to a load of, if we divide the moment by the moment arm, we get the load recalculated as 283.86 Newton. So, in this case, the load has increased because the moment has actually increased to 99.34 Newton meter. Now, let us consider the humero-ulnar joint reaction force. You can see the free body diagram of the arrangement humero-ulnar force, where we have a portion of the applied load taken by the ulna that we have calculated just in the preceding slide. The half of the weight of the forearm as discussed earlier, and we have the brachialis muscle. As you can see here, the inclination angle is already known to us. We need to determine the reaction force at the joint, that is Ru. But one important thing here is included here is the ligament force transferred from the radius. So, the ligament is acting between the radius and ulna, and the line of action is indicated here as FL. So, we can resolve the forces based on the free body diagram, and applying the laws of equilibrium, we can resolve it vertically and horizontally, and we can write the equations accordingly. So, thereafter, we can actually calculate the inclination of the angle of the humero-ulnar joint reaction force, which can be calculated using the two equations and the data that is already available to us. You can see the new updated load Wu has been taken as 283.86, and of course, the limb weight, half of the limb weight is 16.25 Newton. So, with this new data, we calculate the angle as alpha, angle as 5.36 degree, and thereafter we can calculate the magnitude of the reaction force Ru as 1652.68 newtons. Now, with both reactions calculated, the forces acting on the distal humerus can also be determined. We have come at a point that we have two separate joint reaction forces. One is actually the humero-ulnar joint reaction force, the other is humero-radial joint reaction force. Now, if we want to calculate the axial load at the distal end of the humerus, we need the vertical components of the two joint reaction forces. So, one is the Ru joint reaction force and the other is RR joint reaction force. So, the components of these joint reaction forces along the vertical direction can be obtained as stated in the equation. So, we have the cos of x. So, x, the angle x has already been calculated in slide 11. Please go back and you can visit the slide 11 for the calculation on angle x. Angle alpha has recently been calculated as 5.36. X was calculated earlier as 58.85, and we put the respective value of the RR and RU, and we finally get the axial load on the distal end of the humerus as 21.26.62 Newton. Now, this load of around 2100 Newton, that is about 200 kg, is remarkably high indeed, which is about more than twice the body weight. Now, if we consider the cross-sectional area of the cortical bone in the humeral shaft, the cross-sectional area is about 200 millimeter square. So, the mean compressive stress can be calculated as the axial force divided by the cross sectional area, and it comes out to about 10.63 MPa. Now, this stress is actually low compared to the compressive strength of the humeral bone, which is about 864 megapascal. So, let us come to the conclusion of this lecture, both part 1 and part 2 together. What did we learn from the biomechanical analysis of the elbow joint? The joint reaction force, both humeroradial and humeroulnar separately, has now been determined using a rather simplified analysis. The role of the ligamentous system, most importantly, in stabilizing the elbow joint has been identified. However, a more sophisticated examination of the structure would also take into account the muscles passing along the forearm, which must also be active. In our simplified analysis, we did not account for these muscles. So, their role include the grasping action of the hand and stabilization of the hand at the wrist. These muscles largely originate from the epicondyles of the humerus, so they compress the elbow joint. So, this has the effect of moving the reaction force R more in line with the radius bone, so that it will not normally try to sublux anteriorly, as our simplified calculations have suggested. I hope you could follow the calculations presented in this lecture clearly. The list of references are indicated in these slides. It is applicable to the entire lecture, part 1 and part 2, on the biomechanics of elbow joint, and I like to thank you for listening.